Okay, this hour we start our next chapter, transport layer, chapter 3. And again, the goal of this chapter is to understand the principle behind transport layer services. As we mentioned before, on the top is the layer 7, right? Layer 7 is the application layer. You can design your own layer 7 application layer protocol. But after that, when you pass the message from your process from the other process, as we mentioned before, communication actually is belongs to inter-process communication, although it's across the entire internet. Okay, but after you open the socket and you push your message to the socket, the operating system will have certain programs which is responsible for transport layer, and it will receive the messages pushed by your application layer protocol, and then will transmit the segment, as we mentioned before, to include a header. So I think we draw this figure a lot of times, right? Right. Right, we have two sockets right here for each process, and the message will be passed through the socket, right? So the program at the transport layer will need to receive the messages from the above application layer, right? And then send it to the underlying IP layer, which is also in the operating system, right? And all the way to the remote host, and then receive the segment, right? And then send the message through the socket to the application, right? As we mentioned before, there should be a multiple process in your operating system, right? But which one should receive this message? Okay, we mentioned it in chapter 2. We need to identify its IP address, its port number, right? So the operating system knows, okay, which service should receive the segment and the message, right? So that is called multiplexing and demultiplexing. Okay, after that, we talk about TCP, right? So TCP should help the application layer to do several different things. For example, reliable data transfer, as we mentioned, that every bit sent from the application will be virtually sent to the corresponding process, right? Every bit will be checked, right? The order will be checked, so we can do the reliable data transfer. Although these underlying packet switch routers, those fibers, those copper wired, they are not that reliable. But the layer 4, the program at the layer 4, those transport layer protocols should create an illusion that makes the upper layer application, they believe, okay, the underlying layer 4 is very reliable, as we mentioned it before, right? And the flow control and congestion control, the upper layer, the application layer can send a very large message to layer 4, right? But as we mentioned before, all those messages will be divided into several segments, Okay, so they always will send the segments to their three and to the entire internet, right? But they cannot those transport layer, they cannot send those segments too quick or too many, because we don't know who the host receives these segments. We don't know what is the capability of this receiver, how many RAMs they have, what is the bandwidth they have, what is their CPU they have. Can they handle such kind of large amount of segments, right? So they have the operating system at the sender side and the receiver side. They should come up some mechanism to do flow control so that the sender will not overwhelm the receiver. And of course, there are some other routers, right? There are some other routers in the internet. Again, the sender should not overwhelm those routers, because if you send too many packets in the internet, all those routers will the buffer will filled up, right? So they should do congestion control. Okay, so and in this chapter we'll talk about the actual transport protocol, UDP and TCP. Okay, so we skip this slide. Okay, and again we talk about those things many times. Okay, so the transport layer, the transport service, they provide the logical communication between application processes. So that is processes. Okay, inter-process communication among different hosts. Okay, so therefore they care about what process they communicate with each other, but there are three. They cares about sender host and receivers host and all those routers. So different layers has different responsibility. Okay, transport protocol action in end system. In sender side, okay, at the sender side, they will break. The protocols. Okay, transport protocols will break application message into segments, as I showed you before, and pass to the network layer. And of course, they will pack the message into segment, right? Message like this, and they will attach therefore headers, right? And then those segments will further packed by network layer 3 as an diagram, right? And then will be packed by layer 2. So the element is called frame, right? So the frame will be passed through the internet step by step. And then when the receiver receives all those frames, packets, and segments, the receiver will reassemble the segment into message and pass the entire message to the application layer. Okay, so we mentioned it before. Okay, we can pass this one. Okay, so here you can see that again, this is the figure we mentioned a lot of times. Okay, right hand side is the sender, left hand side is the receiver. The right hand side we have application message, and we'll pass the message through the socket, the yellow socket, to the layer 4, and layer 4 will attach a layer 4 header. Okay, it's right here, the layer 4 header. Okay, so the segment will be passed through the its IP layer, and so on and so forth, so on and so forth. And then the diagram will be passed to the destination, right? So the purple one, and then will pass to the corresponding transport layer. So ideally, those transport layer will virtually feel that they pass the segment to each other, but actually it is done by the underlying IP layers, right? And those two applications at right hand side and left hand side, they virtually feel they can communicate with each other by sending those messages, but actually the message is delivered by the underlying transport layer. Okay, we talk about this figure many times. Okay, So again, we have two protocols, TCP and UDP. TCP stands for Transmission Control Protocol. Okay, it provides reliable and order delivery. We mentioned it before, and we have congestion control, flow control. Okay, we'll talk about how the actual program they at both sides, the sender side and the receiver side, how they design several algorithms and procedure to achieve the control, congestion control and the flow control. And as we mentioned before you send the actual message, the TCP socket need to communicate with each other to exchange certain parameters. So TCP needs connection setup, but UDP, user datagram protocol, we don't have any services like reliable data transfer. We don't have congestion control. We don't have flow control. We don't have setup in UDP. And both protocols, they do not provide delay guarantee and bandwidth guarantee. We discussed it before, right? Okay, so that is okay. So let's take a look at the multiplexing and the demultiplexing. As we mentioned before, in your host, in your operating system, there should be several processes. For example, we have three hosts right here, A, B, C. They have different IPs, right? And host A has process 3, host B has process 1 and process 2, host C has process 4. Okay, so they would like to communicate with each other. So let's take a look at this purple line. Okay, so this purple line, the process number 3. Okay, it has a message, a green message. Would like to transmit the message to process number 1. Okay, so it has a socket. The port number is 123, and the destination process P1, okay, has a socket 80. So through the purple line, okay, the message will pass through the port 1 through 3, and header H4 will be attached, right, to form the segment, and so on, so forth, and so forth. Okay, so after the transport layer at the receiver side, which is B, after it receives such kind of message, it will check out the destination port written in the transport layer header, which is the H4. Okay, and it specifies this message is sent from A, P3, port 123 to host B, port 80. So the number 80 will be written in the transport layer header. So the transport protocol can look up the destination port and then unpack this segment and send the message to port 80. So process number 1 will get this message. So that is what we call the multiplexing at the receiver. So use the header info to deliver received segment to the correct socket. So multiplexing means when you send the message, you have to know what is the destination IP address and the destination port used by your corresponding receiving process. Okay, so you have to know that. So before A and B, before P3 and P1 set up this socket, they have to know what port number they use. Okay, this is very important things, very important functionality provided by the transport layer. Okay. So how the multiplexing works? Let's take a look at the right-hand side. That is the TCP and UDP segment. So right here at the the red part, that is the layer 4 headers, which attached on the top of the layer 7 messages. So basically the red part right here, that is the application data, which is the MSG, the message. So here's an example. For example, if it is an HTTP, the get, the first GET white space, this specific command is the first byte in this application data. Okay, or sometimes we use another word, payload. Okay, so layer 4 header is attached on the top of this payload. Okay, as you can see that there are two fields. The first one is called source port number. Second one is called destination number. They are 16 bits field, okay, which is the first two field of the layer 4 header, no matter if it is TCP or UDP. Okay, the first two 16 bits. Okay, one is source port, the other is destination port. So as we mentioned before, because it is a 16-bit integer, so the number you can use is between 0 to 65535. Okay, and we show you a list, right? The port number below 1024, they are commonly used port. You should not use this port number, right? But all the other port number you can use this port number. So the host should identify itself by using IP. We mentioned it before, and the process, they are associated with a socket, and socket has a port number. So when you send your message, you have to specify the port number you use, which is the source port, and you have to specify the port number used by your corresponding receiving process, which is the destination port, right? We mentioned it before. Okay. So here, here we have several different pages right here. But when you, as I mentioned before, when you see connectionless, that means UDP in this textbook. So here, the UDP demultiplexing, the rule of demultiplexing is a little different from TCP demultiplexing. So they're different. Okay, make sure you notice that. Okay, we recall that as you mentioned before, when you open a socket, okay, from the perspective of programming, for example, writing a Java program, you open a socket, you simply just new, okay, you simply just new an diagram socket object. Okay, it is an object, so you can get this object, you can call the member function of this object. Okay, so when you initiate, when you new this socket, you have to specify the port number, which is the source port number you'd like to use. Okay, so that is 12534. That is an example. Okay, and then when you use UDP, okay, when creating datagram to send into UDP socket, you must specify the destination IP address and destination port, so that your UDP socket can be connected to the remote destination UDP socket. And of course, you can specify the host by using the IP address, and also sometimes you can specify by using its domain name. And of course, your operating system will help you to resolve the domain name to the actual IP address. So actually, they use IP address, but you can provide domain name, which is okay, because your operating system can do the domain name can resolve the domain name automatically. And you have to specify the destination port. So most of the time, if you are the initiator of such kind of communication, that means you are a client, right? So the server should use the server port, so that you don't. So for example, if you connect a socket to the remote HTTP server, the remote server code port, destination port should be 80. But when you connect to a DNS server, the destination port should be 53. So usually you don't have to care about the destination port because most of the server use the commonly seen port number, okay, on the list. Okay, so at the right hand side, when receiving host receive UDP segment, okay, it will check the destination port and the segment and try to direct the segment to the socket with that port number. Okay, make sure you read this sentence very carefully. Okay, the following one: the UDP datagrams with same destination port and same destination IP, okay, the black one, will be directed to same socket at receiving host. So make sure you understand that. So we have a figure right here. So here we use UDP. Don't forget these things. Okay. So we have 3 hosts right here. 5, 6, 7, 8, 1, 2, 3, 4, 3.4, 5, 6 with 3 different hosts, right? Okay. Take a look at this specific line right here. So we have error right here. So this blue line specify host 567 would like to send a UDP message through a socket which is owned by process number 3, and the UDP socket is 9157. Okay, and it would like to talk to host 1, 2, 3, 4, and here is a process, and its UDP socket is 6428. Okay, that is the setting. Okay, so right here, the packet, the UDP packet, okay, its source IP is 5678. Destination IP is 1234. Source port number is 9157. Destination port number is 6428. Right? Okay. So at the receiving side, it's right here. Here is a program, transport layer program. When it receives such kind of we say green packet, okay, when it receives the green packet right here, it will deliver to process number 1 because process number 1 has owned this destination port 6428, right? Okay, and you can take a look at this purple one, this one. Okay, again, the purple one right here again. Let's take a look at this one. The source IP is 3456. The destination IP is 1234, right? But the source port right here, that is 5775. And the destination port is 6428, right? So process number 1 would like to talk to process number 1. So under the UDP rule, okay, take a look at this one. We pick this one, okay? UDP diagrams with the same destination port and of course with the same destination IP will be directed to the same socket at the receiving host. So in this case, although the sender of the green packet and the purple packet is different, but the destination port written and the therefore headers, no matter it's in the green headers or in the purple header, they both say they would like to talk to destination port 6428. So the transport layer, the blue programs in the transport layer, they will deliver these 2 packets, although they are from different source, but they will deliver these 2 packets to exactly the same socket, which is 6428. And this socket is owned by process number 1. So process number 1 will get the green message and the purple message. And of course, there's some other information for process number 1. So process number 1 will know this this process is from 5678 or is from 3456. But this socket, it has only one socket, right here, right? It is an object, right? It is an object. This object is owned by P1, and P1 will receive 2 different packets from 2 different hosts, but P1 will get these 2 messages. So right here, again, let's take a look at this one, okay? Diagram, IP diagram, IP UDP diagram with the same destination port and the same destination IP will be directed to the same socket, okay? Look at the blue part, but different source IP address and or source port numbers. It really doesn't matter what is the source IP or the source port used in this packet, as long as the destination port is the same. So the socket will be the same. So for UDP, okay, so for UDP, no 2 processes in a single host can obtain the same UDP socket, because there's only one UDP socket with the specific number, for example 6428. It is impossible for 2 different processes to use the same socket. Why I say so? Because for TCP, the demultiplexing rules is totally different from UDP. Okay, right here, the TCP socket is identified by 4 tuples: source IP, source port, destination IP, destination port. However, for UDP, the only thing you need to care about is the destination port, and destination IP. But the destination IP is the same, right? So you only care about destination port number for UDP socket. So take a look at this figure, okay? That is for TCP. So again, we have 3 different hosts, A, B, C, right? We have several different processes on different hosts. So take a look at this one, this purple one. You can see that the direction is bidirectional, and you can see that for this one, okay, for this one, when P1 wants to send a message to P4, okay, so the purple line right here is that the source IP here, okay, the source IP is B. The source IP is B. Sorry, the source IP is A, is right here. Sorry, the source IP is A, and its source port is 9157. Destination IP is B, and the destination port is number 80. So the message will go through this purple line. So at the opposite side, okay, if the transmission is from B to A, the source IP is B, source port is 80. Destination IP is A, the destination port is 9157, right? However, you can see that the green one. Okay, you can see that in this transport layer at B, okay, you can see that 3 sockets, their socket number are all 80. They are all 80, right? That is because for this green one, for example, this green one, although at the receiver side for P6, its port number is also 80, but take a look at the source. But the source address is C, right? It's right here, this one. The source address is C. The source port is 5775. The destination IP is B, and destination port is B80. although this part, okay, this. Although this part is exactly the same, right? The destination IP is B and the destination port is 80, but the source is different. According to TCP's demultiplexing rules, any value of this four value, source IP, source port, destination IP, destination port, as long as they are not exactly the same, they are different sockets. So P6, this process can allocate a socket at number 80 as long as it connects to some other IPs and some other port. It is okay because they are different, because TCP distinguish different ports by using 4 fields: source IP, source port, destination IP, destination port. Okay, so they are all different sockets at address B. Okay, so I think that is the I think you can comprehend this. It is very different from TCP and UDP. Okay, we will teach you how to write socket programs after midterm. Okay, so we will talk about the things later. But I would like to share something with you, is that in modern programming language, usually we don't, even if we have 3 different processes, P4, 5, and 6, want to communicate with different process P1, P2, and P3. Usually when we write a server, we simply just use one single process, and then we make it as a thread server. Okay, we draw a thread server like this. Okay, a thread server. Those threads are somehow independent with each other. So each thread, they can new, or they can get an socket object. Okay, and use the socket object to communicate with the remote processes. Okay, usually we use we don't want so many processes in our server. So basically we use a single server, a single process, and we use a threaded server to create different threads within only one single process, and use these threads to communicate with the remote processes, which is okay. So after midterm, we will teach you how to write a threaded server. Okay, basically it's I think it's an example of HTTP. You can use this example to run thread server and communicate, use exactly the same destination port to communicate with each different processes. Okay, so there are 2 different scenarios. Okay, so that is the introduction to the demultiplexing and the multiplexing. Okay, so we will go to next topic, which is UDP, user diagram protocol. In our textbook, UDP is relatively I say easier to understand. So we introduce UDP first, and we will not actually talk too much things about UDP. So let's take a look at the content. Okay, the first one, okay, that is transport protocol, right? UDP does not care about any lost or out of order delivery. So we use a word best effort to describe such kind of services, because UDP simply just try its best to deliver the UDP segment from the sender to the receiver. But if there's anything wrong with the segment, for example, the segment is dropped by the server, the segment lost, the segment is out of order, the UDP does not deal with those problems. Okay, so again, when you say connectionless, that indicates we are talking about UDP. And again, it has no handshaking between the sender and receiver, and each UDP segment handles independently of others. So it's more like it is not that appropriate to describe UDP like this, but it's more like non-persistent HTTP. It simply just has one request and one reply using UDP, and that's all. UDP does not deal with any other things. Okay, so while there is a UDP, because there is no connection establishment, so we don't need to take time to exchange parameters, exchange messages between exchange parameters between before sending the actual message between the sender and receiver. Okay, it is much simpler. So no connection state at the sender and receiver, the smaller header size, no congestion control. So to implement a UDP protocol in your operating system, it is much easier than implementing TCP. Okay, so here is the IFC 768, but we can skip this one. Okay, and again, right here, SNMP is a UDP protocol, but we will not introduce SNMP in the text in our slide, because textbooks just simply does not introduce anything about SNMP. So it's just an example, right? We have SNMP message, and it will go through the socket and pass the SNMP to the UDP program, and we'll attach the UDP headers right here in front of the message and send the message to the underlying IP, and so on and so forth. And after we receive the SNMP segment, and we will unpack the transport layer, will unpack the diagram to segment, and then unpack again, pass it to the application layer. Okay, we talk about these layers many times. Okay, and again, right here, the UDP header. The UDP header is very small. Okay, as you can see that here we have application data, which is the payload, or we say it is message, right? At message, or layer 7, or code payload. You could use any name. Okay, they are interchangeable. Okay, there are only 4 fields included in the UDP header. Each field has 16 bytes. And as we mentioned, you should include the source port number and the destination port number, right? So they are both port numbers. Okay, you have to specify that. And since it is 16 bits, right? So the range is from 0 to 65,535. Right, you have to choose one of the number as your source port, and the destination port specified by the destination, right? Okay, so the third one is the length. So when your layer 4 program receive this segment, this entire segment, right, from layer 3. Okay, so the layer 4 program will parse this segment. So the first 16-bit is the source port, the second 16-bit is the destination port, and the third 16-bit is the length of this entire segment. So right here, in bytes of UDP segment, including header. And right here you can see that the UDP header has only 4 fields. In total, it is 16 4-bits, right? Or 8 bytes. The UDP header. Okay. they are all fixed field headers. They are not variable length, so only 64 bits or 8 bytes. Okay, so if it is a segment that does not carry any payload, okay, which I mean right here, if this segment does not carry any payload, so the size of the payload is 0, but you still need to write 8 right here because we have 8 bytes, right, in this entire segment. But the 8 means the TCP belongs to the TCP headers, and the layer 7 payload is 0. So the minimum number of this field is 8, not 0. Okay, because it includes the UDP header. Okay, and so what is the maximum number of this value? It should be 65535, right? But if it is 65535, the payload carries in this very big segment, the size should be -A, right? Sorry. The maximum layer 7 message payload of a UDP segment is 65527. That is the maximum size of the payload that can be carried by a single UDP segment, right? Because the length has only 16 bits, the maximum number can be written in this field is 65535, but it includes the header, right? So that is a number. But actually, it is just a theoretical number. But actually, in layer 3, the layer 3 packet is a little bit smaller than this number. So in reality, in real world, a segment should not that big. Okay, should be smaller, much smaller. We'll talk about this number in next chapter in layer 3. Okay, so the next header field is checksum. Okay, so it's right here. Although, as we mentioned, although UDP does not provide any guarantee about bit error, but it still has certain level of reliability designed in the TCP header, UDP header. It is UDP checksum. The goal is to detect errors. Errors means any flipped bits in the segment. You have to notice that we detect all those errors in UDP, but we do not correct those errors. We simply just detect if there's any bit errors. We don't UDP. I mean UDP. UDP does not try to correct those errors. If any errors is found in the UDP segment, your layer 4 program, your UDP protocol will simply just throw away. You'll simply just discard this UDP segment. Okay, let's see. From the sender side, okay, treat content of UDP segment, including these headers, IP addresses, as a sequence of 16-bit integers. Okay, the checksum means we add all those 16-bit integers to get its sum. Okay, so for example, if I have a segment like this, okay, so basically we can divide it into several different part. Okay, each part is a 16-bit field. So we add this we add the first part and the second part, third, fourth, fifth, and so on and so forth. So for the entire segment, we fragment all those bits or bytes, okay, into a lot of 16-bit integers, and we add all of these bits together to calculate its checksum. The actual operation is right here. So here, for example, we have two 16-bit integers right here. So you simply just add them, okay, by using, okay, it's right here, one's complement sum. Okay, so I believe you know how to add two integers bitwise, okay, bitwisely. So 0 and 1, right? So the answer is 1. 1 and 0, the answer is 1. 1 and 1, the answer is 0, and the carry is 1. So 1, 0, 0, and the result is 1, and so on and so forth. For example, right here, 0 and 1, and the result is 1. 1 add 0, the result is 1. 1 add 1, the result is 0, carry 1. 1, 1, 1, the result is 1, and carry is 1. So the result is 1. But you can see that because of the carry bits, so the answer is 16-bit. 1 bit larger than 16-bit, right? So we have a rule right here. If we have one more bits right here, we simply just put this value to the end of this result, and then 1 and 1 is 0, carry 1. 1 and 1 is 0, carry 1. 1 and 0 is 1, and so on and so forth. So the result is right here. You can simply use this way, okay? Add two 16-bit integers, and if there is one carry bit, okay, wrap around it to calculate the sum, and then we flip all those bits. So 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0, 1, and so on and so forth. So the checksum is this value. Okay, that is how you do how do you calculate the checksum. Okay, so for a segment, right, you have a lot of 16-bit. You simply just add them all together and follow the rules. Okay, if there's a carry, do wrap around, okay, and calculate sum, and at the end you calculate the checksum by flip 0 to 1 and 1 to 0. So that is the checksum. So after you calculate your checksum, you put the value right here, and then the UDP segment is created, is done, and you can send this UDP segment to layer 3 as a sender. Okay, so we put into the UDP checksum field. So by this way, as a receiver, you simply just repeat all the calculation at the receiver side again, and you check if the compute checksum, okay, first, not equal to the checksum that calculated by the sender, then you know there must be something wrong. There must be something wrong with the bit you received from your layer 3. So error detected, right? If the receiver, the computed checksum at the receiver is exactly the same as the value calculated by the sender, and we say no error detected. So we have a very simple mechanism to check if there's any error bit in this specific segment. If no errors, then the segment will be unpacked and the message inside the segment will be sent to the upper layer, to the application layer. But if there's something wrong with this segment, so we detect the bit error and this specific segment will be dropped by the receiver's therefore protocol. Okay, so the message will not be sent to the upper layer because, as we mentioned before, UDP does not guarantee any reliability. So the UDP can drop this packet, and the UDP does not need to inform the sender because they don't have such kind of mechanism. Okay, but we have a interesting like to share with you is that since we use the addition operation to do such kind of checksum, but as you can see that when you do such kind of 23, we do addition right here, but even if the numbers right here is different, there's some possibility that the result is exactly the same, like the example I write here, right? So sometimes, okay, right here, even if the result calculated by the receiver is exactly the same as the value calculated by the sender, we do not we say it has a very small chance that this condition, this problem happens. Sometimes the bit at the receiver side, it actually has bit errors, but the addition, the checksum, maybe, I say maybe, okay, maybe still exactly the same as the sender's value. But it has a very small chances, very small chances. But it's okay if it really, in these cases, and then let it be, okay? But it is some coincident. Okay, so that is the checksum. So that is the last slide of UDP, and we stop right here. We will continue TCP next hour. And as you can see that in this textbook, we don't mention much about UDP, but we simply just tell you what is the format of this segment and the very interesting mechanism called UDP checksum in UDP. Okay, we stop right here.